Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about trigonometric equations. We are going to solve them all kinds of ways. It is going to be great. While this song is not from Dave's Faves, I wanted to give him one last tribute. Dave's Faves, hot CD out, produced by the great Darby Foster. So let's get to it, shall we? That song is The Way by Fastball, and the way is through mathematics. So, linear equations here have exactly one solution, and quadratics can have at most two real solutions. But trig equations generally can have an infinite number of solutions, and if you think about that, if I have a sine curve or a cosine curve that goes forever and ever, and I have a horizontal line, well, there's 1, 2, 3, 4, 5, 6, 7, 8 solutions there in just a few cycles there, just 1, 2, 3, 4 cycles, or not 4 cycles, 4 humps. So we're going to use these, and we're not going to do the pre-prepared graphs, but we're going to take a look at technology and, of course, algebra. That is where students generally find the most difficulty is solving trigonometric equations using algebra. Okay, so here's things. Here's a first example. Solve 2 sine x minus cosine x equals 4 minus x for 0 less than or equal to x less than or equal to 2 pi. We use the inspire, so we should set our calculator to see from 0 to 2 pi, one period or so. This looks like a bit more. So we graph 2 sine x minus cosine x, bam. We graph 4 minus x, bam. And it's from 0 to 2 pi. And so we get the intersection points. Now, they just got the 5.81 here, but you would also have to find this one and this one. So there are 1, 2, 3 solutions on the interval or in the domain of the function. So we know how to do that. We'll talk about that more in class, but that's easy peasy. Okay, so in solving trigonometric equations using algebra, there are times, well, let's take a look at sine x equals 1. Okay, that's an equation. That's a very simple equation. We know that sine is equal to 1 at pi over 2. Well, depending on the domain, I might have to name pi over 2 plus pi, go around again, plus 2 pi, plus 3 pi. In other words, I can get that solution every pi over 2 plus multiples of pi. So that would be a solution where I have to go full around the circle, and I can say that the solution, or all solutions, are given by x equals pi over 2 plus k times 2 pi, right? I think I said pi earlier. I meant 2 pi because I went all the way around the circle. For any k, an element of the integers. So all that is saying is any multiple of 2 pi starting at pi over 2 is going to get me right back to pi over 2, whether I go in a positive direction or negative direction. And sometimes we can just go k pi units. For example, we know that tangent is equal to 1 at positive 1 at pi over 4, as well as at 5 pi over 4. Well, they're only pi units away. So instead of k2 pi, we can do k pi. Let's do some examples. Okay, so notice we've got our unit circles here. Unit circle, they just split them up into 2 because it was getting a little crowded. These 1 over root 2's, we think of them as, or we've talked about them as root 2 over 2. They are equivalent, and if you want to use 1 over root 2, it's perfectly fine. Just wanted to point that out. These will not be available to you. You must know your unit circle. So to solve this one, we need to, just like any other algebra algebraic equation, we have to isolate the x variable. And in this case, we're isolating sine x. So I add 1 to both sides, divide both sides by 2. And the question is, where does sine x equal 1/2 from 0 to pi? So that's only from here over to here. So this is where there's no magic thing to get the answer. I have to know my unit circle. I have to know where sine is 1/2. And of course, that is right here from 0 to pi, and also right here. What are those? Those angle measures are pi over 6 and 5 pi over 6. Done. Boom. There you go. For this one, tangent x plus root 3 equals 0. So tan x is equal to negative square root of 3. So we have to think about that, where that happens. So while we didn't memorize or derive where tangent is equal to the square root of 3, you will get quite used to it, or negative square root of 3. But we just need to look for the root 3's. Now remember, tangent x is equal to sine x over cosine x. Okay? And I will tell you just right off the bat that the solutions are equal to, oh, this is for 0 to 4 pi, but I'm just going to do 0 to 2 pi in just a second. So I will say the solutions between 0 and 2 pi are 2 pi over 3 and 5 pi over 3. Okay? So tangent x equals sine x over cosine x. 2 pi over 3 is negative 1/2 root 3 over 2. So that would be root 3 over 2 over negative 1/2. The halves cancel and I'm left with, or not the halves, the 2's. So that would be equal to negative root 3. Okay. Now I also have 5 pi over 3, which is right here. Now they don't have the same exact values, but one is positive and one is negative. So clearly that is also going to be a solution, or equal to negative root 3. So this says between 0 and 2 pi. So in order to get the next solution, if I travel from 2 pi over 3, another 2 pi units, I'm still within 0 and 4 pi. Because if I go around twice, 2 pi, 4 pi. So clearly that is going to be within our domain of 0 to 4 pi. So I have to think, oh, okay, what's 2 pi over 3 plus 2 pi? Well, you can do it in your head if you think of 2 pi strategically. Since I have a denominator of 3, I'm going to think of 2 pi as 6 pi over 3, getting the same denominator. So that gives me the next solution of 8 pi over 3. Using the same strategy for 5 pi over 3, I'm going to add 6 pi over 3 and get 11 pi over 3. How do you know where you're done when you're done? Well, you either keep track as you go around the unit circle, or you realize that 11 pi over 3 is very close to 4 pi. And 8 pi over 3 is kind of close. But if I travel, let's just say the smallest one, if I add 6 pi over 3, then I'm at 14 pi over 3. And 14 divided by 3 is certainly greater than 4. So you know that these two are going to be the last two solutions that work in your domain. On another note, let's talk about tangent. Okay, so we know tan at our pi over 3's is going to equal either positive or negative root 3. The only other ones that we really need to worry about are at our pi over 6's. Okay, and we should keep these in our back pocket. Well, instead of root 3 over 2 over 1/2, at pi over 6, sine over cosine is 1/2 over root 3 over 2. Again, the 2's cancel. So I have 1 over root 3, which is a perfectly acceptable answer, Or if we rationalize the denominator by multiplying by root 3 over root 3, I get root 3 over 3. Okay, so this is equal to plus or minus 1 over root 3, which is equal to plus or minus root 3 over 3. We should just know these so when we get tangent equations, we can solve them fairly quickly. Okay, and then I don't have to worry about my pi over 4s because those are all going to be plus or minus 1. And then tangent is undefined at pi over 2 and 3 pi over 2 because cosine is 0 there. And then it would be 0 at 0 and pi and 2 pi. So those you got to kind of think about, but as you solve more tangent equations, you should be used to it. All right, let's take a look at one more. We're going to have to split this up. Solve exactly for 0 to 3 pi, sine x equal to -1/2. Well, sine x equals -1/2 at our pi over 6's, right? So that would be x equal to, let's see, 7 pi over 6 is the first one. And then the next one is 11 pi over 6. Now, let me just stop for a second. When they say exactly, they mean don't put this in your calculator and give a decimal approximation. This is an exact answer, okay? So we're going between 0 and 3 pi. So if I travel 2 pi units around here, starting from 7 pi over 6, 7 pi over 6 plus 12 pi over 6 is 19 pi over 6. Okay, but 19 pi over 6 is greater than 3 pi. So that's out. And so I know the multiple of this is also out because that would certainly be greater than 3 pi. You also know that because if you just think about it, from here around to here is 2 pi, and then another, if I just travel pi units, I'm here, right? So if I travel here, this is my first solution, and I go back around 2 pi, once I pass 3 pi, I know that I am done. All right, I think I'm going to stop there. This will be part 1. And we shall look forward to part 2. Hope you enjoyed it. I know I did. And with that, I am out.